Okay, so welcome to Math Surgery Wikispace's introduction to logarithms, and in this section of the lesson we're going to be looking at the following lesson objective. We want to be able to change the base of logarithms to help us evaluate logs using a calculator and to solve equations. And this is the first video of a set of 5. This one just outlines what we're trying to do. The next one will have a proof of the key things we're going to need to use to be able to work through C2 Chapter 3 exponentials and logs. And if everything goes right after the 4 video lessons that follow this, you'll be able to evaluate logs by changing bases and solve log equations involving different bases, and you'll complete C2 exercise 3F with me. Okay, so in exercise 3F we're going to be using the law that log base A of x is equal to log base B of x over log base B of A. We'll find out in a minute why you'd want to use that, but first of all let's make sure it's true. So log base A of x must be equal to something. Let's call that thing m. Now log base A of x equals m means that a to the power m was equal to x by the definition of what logs does. It undoes powers, doesn't it? So that means that a log of a to the power m must be equal to a log of x, simply taking logs of both sides. If the two sides are equal, the log of both sides are equal, whatever base we choose. Now I'm going to choose base b, and that means that log base b of a to the power m is equal to log base b of x. We can use the laws of logs to bring the m to the front, giving us m log base b of a is equal to log base b of x. And we're going to simplify that to get m on its own. So here's the rearrangement. M equals log base b of x divided by log base b of a. At which point you might realise that m, of course, was equal to log base a of x. So I'm going to delete the m and replace that with log base a of x. And this little guy, log base a of x is equal to log base b of x over log base b of a, is what we set out to prove. So we're happy with that. So why would you want to know? Well, because you want to be able to change the base of logarithms. Until fairly recently, we would have to change to log base 10 or log base e to do any calculations, because calculators didn't have a log base one thing of another button. Nowadays they do, but in the old days we'd have big tables of logs, and here's one which has got a table of logs base 10. Modern calculators do allow us to use log base one thing of another. So for instance, log base 2 of 1024 asks what power of 2 gives us 1024, and you may well know that's 10. Fair enough, but if I say what's log base 2 of 1000, that's less obvious. It's going to be a little bit less than 10, but exactly what would require a calculator to find out. And that's why we need to be able to change bases of logs, so that we can calculate one log of another base without necessarily using that button if we don't have it on our calculator, but also so that we can solve more complicated problems later. Okay, so let's see that in action then. So we want to calculate log base 2 of 1024, and a moment ago we did that on the calculator. We even worked out that we knew what that was already. So log base 2 of 1024 came out to be 10, because we know that 2 to the power 10 is 1024, and we worked out log base 2 of 1000. So log base 2 of 1000 was 9 and a bit, in fact 9.9 if I remember rightly. Let's see what that says. Yeah, 9.96 and some small change, 5784285. But we're cheating, aren't we? Because we're using the calculator using the modern button. What if we were to do it the older way? Well, we'd rewrite this log base 2 of 1024 as being equal to log base 10 of 1024 divided by log base 10 of 2. It would be worth us just checking that that actually comes out to be the same thing. So here is log base 10 of 1024. And we're going to divide that by log base 10 of 2, and with a bit of luck we get 10, which we do, and going back into that we can change that 1024 for 1000, and we get the 9.9 that we expect. So that's the way we should have done it originally, that log base 2 of 1,000 was equal to log base 10 of 1,000, which is actually something quite nice, isn't it? That's going to be 3 exactly, divided by log base 10 of 2. So that's the way we ought to do it. Now, you can choose which you want to do, but it's worth being able to do both, because the second version is going to come in useful next. Okay, so far so easy, but in question 3 things rack up a little bit and things get a bit more tricky. Before we start, we're going to derive a little useful rule, which is that given that we know that log base a of x equals log base b of x over log base b of a, if we substitute x equals b, then we've got log base a of b is equal to log base b of b divided by log base b of a. And a moment's thought should make it immediately obvious to you that log base b of b is 1. And so if we want to swap bases, log base a of b is the reciprocal of log base b of a. And that's going to be very useful in a moment. It comes in useful on this example here, where we've got log base 3 of x plus 4 log base x of 3 equals 5. So this is awkward. We've got the 3 and the x the wrong way round, so we simply swap them by using the reciprocal rule, and we've got 4 over log base 3 of x on the denominator there. We can now substitute y for the log base 3 of x, just so that it's clearer to read, and it becomes obvious that what we've got is a slightly transformed quadratic. If we go through and multiply everything by y, we get this. We can solve that quadratic by rearranging it into its standard order, factoring it. So we've got y minus 4 and y minus 1 equal to 0, meaning that y is either 4 or 1. And then we remember, but hang on a minute, y was log base 3 of x, and if that's equal to 4 or 1, we can then solve that by thinking if we've got base of 3 to the power 4 is equal to x, then x equals 3 to the power 4, which turns out to be 81, or we've got x is equal to 3 to the power 1, which is obviously just 3. So we get 2 solutions from that because it turns out to be a quadratic. Okay, so in the second example of this type, we're going to use that rule in a slightly different place. Here we've got 2 different bases, and we need to have a look at the bases, and a bit like we might when we're looking at adding fractions and we're looking for a common denominator, here we're looking for a common base. That is to say, a base number to which both of these are powers. Now 3 to the power 1 is 3 and 3 squared is 9, so it's kind of obvious here, but if that were, for the sake of argument, 32 and 512, you'd have to realise that, that those are both powers of 2, for instance, and then you could write them all in log base 2. But here with 3 and 9, it's fairly obvious that log base 3 is the way to go. What we're going to do is leave that log base 3 of x where it is and transform the log base 9 of x into log base 3 of x divided by log base 3 of 9 using our first rule. Now, log base 3 of 9 asks what power of 3 makes 9, and we know that's 2. So we're dividing by 2 here. And things suddenly become a lot easier. We've got log base 3 of x, add the log base 3 of x over 2 equals 5. We can go through and double everything. And that comes out to be 10. So we've got 3 lots of that thing on the left-hand side. 3 log base 3 of x is equal to 10, meaning that we've got log base 3 of x is equal to 10/3. We remember that logs mean what power of this number gives us that answer, so we're asking 3 to the power 10/3 is equal to x, and with a quick bit of calculation we can find that 3 to the power of, we can even put a fraction in there, can't we, 10 thirds is equal to 38.94. So x equals 38.94 in a little bit, and that's probably good enough for now. So that's the way we deal with those. If you've got two related bases where one is a power of another, or they're both powers of a third thing, then what you need to do is change the logs to the base of the thing that goes into both of those, and then you can work it from there. Okay, off you go, have a go at exercise 3F.